Now let's look at the chemistry in translation more in details. This is the structure of tRNA. So tRNA, as you can see here, is a quite big RNA molecules. And then some partial structures here that are connected together through Watson and Crick at the base pairing. So there's some partial complementary sequences, they form up together and they form this kind of a secondary structure of tRNA. And this is three-dimensional the model of this molecule. And simply, even you can draw this way too. Now as you can see here, tRNA has also the direction from 5' to 3' direction. Now this is the 3' end adenine group. Can you find the 3' hydroxy group? So this is adenine group attached to the sugar. This is a 5-membered ring of ribose, and maybe this is hydroxyl. This is connected to phosphate bond, and maybe this is oxygen in the ring. Then can you count? So directly attached position is 1', 2', and 3'. This is the 3' hydroxy groups. So from now on, you may think you are familiar with this chemical structure, but even by looking at those models, if you can figure out by those shape, okay, this is purine, adenine, and then this is ribose, and if you can find these positions, that would be really nice. Now let's think about the peptide bond forming. So for making the peptide bond, you have one amino acid and another amino acid, and the reaction should happen between this carboxylate and amine group to make a peptide, right? If you do this reaction chemically, which group would you like to activate? Amine group or carboxylate group? Think about the chemical method you can choose. Most likely in this case, amine group, nothing much we can do. So usually we activate carboxylate group because this hydroxy group is a bad living group. So that's why somehow we need to change this hydroxy group into good living groups in chemistry. Nature utilizes exactly same strategy. So this is amino acid and this is a carboxylate. And nature utilizes ATP as activating group. ATP is biological energy source by providing this activated bisphosphonate group, and by providing this can attack here, and then by releasing pyrophosphate, it can form up this kind of activated the intermediate. So this is similar to anhydride structure, right? If it's a carbonyl here, that's what we call anhydride, which is one of those tricks we can use to activate the carboxylate group. In biological systems, utilizing ATP, they make up this intermediate amino acid AMP groups. Now here, this is tRNA. tRNA's adenine group, we just found out that 3 position hydroxyl group, right? So this hydroxyl group attack this position, releasing of this whole AMP. And then this amino acid group is loaded on tRNA. Do you see that? So this adenine group and the end position of a tRNA adenine group is not same adenine. So this has been used as an activating group and just loading of this amino acid, and then transfer this onto tRNA, and then AMP is removed. Okay, so this is how the amino acid tRNA is synthesized. And this reaction is catalyzed by enzyme so-called amino acyl tRNA synthetase. So first step is this enzyme recognize amino acid and then take one ATP as a cofactor and activate that amino acid and take up to the tRNA and then transfer this amino acid group to the tRNA. And then this amino acid tRNA is ready to go for protein synthesis. So this cycle can be recycled here. As we have 20 different amino acids, how many different tRNAs do we need? So we can think easily, at least we need to have more than the minimum 20 tRNAs, which should recognize each different amino acids. Then, how many amino acid tRNA synthetase do we need? This enzyme should recognize different amino acid, and at the same time, it should recognize different tRNA. So again, minimum we need to have minimum 20 different amino acid tRNA synthetase. Now, if you think about those the coupling of the step, now this is tRNA coming in. This is A site, and this is a P site. Now this is moving to this direction. So new tRNA coming in, and this is a growing chain. Again, this is N-terminal. This should be C-terminal, right? Now the chemistry is this one. Whole group is connected to this tRNA through ester bond. Now new coming guys, this one has bound ester, and also it has a free amino group. Now free amino group can act as a nucleophile, and it can attack this position. That means this whole group is shifting from here to here. Actually, it's a little difficult to say. This whole group is moving. Actually, this group is moving out and then pushing this out and then replace this bond. That's more correct, the event that's happening here. So this whole group is moving in, and then nucleophile attack here, take over all this the growing polypeptide. So again, this one, the direction wise, this one is N-terminal here, and then this is a C-terminal. Even though nucleophilic the addition happens from this side, the end group here is carboxylated group. That's why this is a C-terminal. This is the chemistry happening in ribosome.